As we get into nuclear chemistry, this is when it's no longer ordinary chemical reactions. Okay? So law of conservation of matter states that matter can't be created or destroyed in ordinary chemical reactions. Now this kind of goes out the window, so to say. Okay? Now we're talking about the changing in the nucleus, which means numbers of protons can change. Up until this point, we've looked at electrons and neutrons. Neutrons, now we can also have protons change. So they're becoming another element, guys. Nuclear chemistry is where new elements are being formed. All right, it has nothing to do with electrons. Take a look at it. It's just protons and neutrons, since those are the ones dealing with nucleus. Now, even though I say it has nothing to do with electrons, we're going to see that one specific type of radiation does deal with electrons. Okay, we'll get there in a little bit. So, talking about stability of nuclei. Large atoms, guys, which means typically we're looking at the elements that have an atomic number that's greater than 83. So like I was saying, typically, guys, large atoms, bigger than 83, they are naturally radioactive because they have an unstable nucleus. So if you were to take a look at your periodic table, if we were to go through, just take a look at your periodic table. If you look at those ones greater than 83, those elements that are larger than 83, so let's say, for example, let's look at like francium, all right, 87. What's the mass on 87? 223. Now, the higher up you start getting, guys, what's changing to make the mass different? So that's a review question. What's that? Neutrons. Neutrons? Just neutrons? And protons, right? So they're the two that will have a mass value that change the mass of your atom. Okay? Now, what do we know about protons? They're what? They're positive. Do positive charges want to stay together? Is a nucleus small or large? Just in general. In the relative scheme of size of the world, they're super tiny, right? Super, super tiny. Well, you've got all these positive charges, guys, in a very, very small, densely packed space. They don't want to stay together. So it starts to take more neutrons to help offset that charge of the positive ones. So if you start looking up until the middle of the periodic table, typically you have about 1 neutron for every proton. But the more higher up you get, then you have to start adding extra neutrons into that nucleus to keep it stable from breaking down. But eventually you get to a certain point where, hey, they just want to naturally break down over time. And that's what we're talking about here with the large atoms. Greater than 83, they are naturally radioactive. They have an unstable nucleus. Okay? So if you take a look, after 83, so starting at polonium, what do you notice about all of the atomic masses in those boxes?
They're in parentheses.
Yeah, they have their whole numbers and they're in parentheses. Okay? All the other masses less than 83 have decimals. Review question here, why are they decimal numbers? They're averages of all the naturally occurring isotopes, right? Here, when we take a look at those ones greater than 83, guys, they're giving you the most common, or the most stable isotope. So they're just giving you one isotope number because they're all radioactive. They're going to break down. So they're giving you the most stable isotope. That's why they're in parentheses. Small atoms, their nucleus is typically stable. They're not naturally radioactive if it's less than 83. There's some exceptions to that where it's a small atom rule. When an atom's mass is not its typical mass, that's when it's an isotope of the mass seen on the periodic table. The atom is radioactive. So something like carbon-13 and carbon-14, they are going to break down. Where have you guys heard carbon-14 before? Carbon dating, right? That's how they date different things. Is based on the relative abundance of carbon-14 in those samples. Okay. So radioisotope, guys, is an isotope of any element that is unstable and therefore radioactive. Table N. Flip to Table N in your reference packet quickly. Okay. Table N is a list of radioactive isotopes. So looking at Table N, it gives you the nuclide, which is just the isotope that is radioactive. It gives you the half-life, which we'll talk about half-life this week. I'm sure you guys have all talked about half-life in earth science before. Is that true? Okay, so you have some familiarity with that. It gives you the decay mode. That's a new piece that we will get into. And then it also gives you guys the nuclide name. All right, so this is where you take the name. Specifically, what is that notation called with that name, where it's got a dash with a number after? This is a review question. We've seen it before. This is the one that I also told you when we did the different notations. This is the one that people would forget the most. It's called hyphen notation, right? Where after the hyphen gives you the specific isotope that they want you to look at. Okay? So it just gives you all that information. Be aware of it. Know where it is. We'll use it over the next week or so. All right, let's move on. Like I said, I'll give you guys what needs to go in those blanks tomorrow. Transmutation. Okay? Transmutation is the next piece. All right, transmutation, guys. You're changing, okay? You're changing the nucleus of one element into the nucleus of another element. So you're either gaining or losing nucleons. What do you think that term nucleon means?
More than one neutron.
What particles?
Protons.
Or?
Neutrons.
Guys, they're particles in the nucleus. Okay, so that term nucleon means particles in the nucleus, which, like you said, would be protons or neutrons. So you're gaining and losing protons and neutrons. Always decays into a more stable element. That's the key. So when you hear about nuclear radiation, okay, what's happening is you are losing protons or neutrons in your nucleus, or you're adding some in, okay, depending on the type of nuclear decay that's happening. But it's always yielding a more stable element. Okay, a more stable element. That's the name of the game here. It's going from something less stable to something more stable. Kind of like our exothermic reactions, right? Which, again, you can kind of think why nuclear power can be harnessed is because it's releasing energy a lot of times. Now, there's different types. We'll talk about that. But that's one thing that we can kind of tie it into. All right, so natural transmutations. These happen, again, with unstable atoms. These are elements, guys, again, that are the large ones above 83. So, for example, all right, I'll let you guys get this down and then we will discuss it. So between today and tomorrow, we're going to be discussing the types of decay. Okay? This one that's shown here, guys, we've got uranium-238, which is an unstable uranium isotope. So what's going to happen? Naturally, it's going to give up what we call an alpha particle. We'll talk more about this tomorrow in the details. Okay? But a new element's going to form. So the name of the game here, when we're talking about radioactive decay, is that, again, conservation of matter, quote unquote, whatever's on the left side of the arrow, you've got to add up everything on the right to be equal to the left in terms of mass and atomic number. So alpha particle we're going to learn about, that's just a helium atom. Excuse me, not helium atom, a helium nucleus being given up. So we're going to figure out what the new element's going to be. All right? Now, everything on the right side, over here, on the bottom lines, which are our atomic numbers, and the top, which is our mass numbers, review, we've done that, we should know that, they've got to add up. So, basically what we're going to do here, if we're looking for the new element, we're going to subtract these numbers to give us our new one. That's the way to think about it. So what's the new mass number going to be of our new element? 238 minus 4 is going to be 234. What's our new atomic number going to be?
90.
What element has atomic number 90? Thorium. You know, when he's not too busy, saving the universe, he's decaying. Huh? Get it? That was really bad, right? Yeah. So, guys, that's what happens here. We'll talk about the different modes of decay as we go through, but that's what we're doing. Okay, to write a nuclear reaction is what are the elements that it breaks down or breaks up into after it decays. Now, let's say that this new element, that could also be radioactive. So what do you think is going to happen with that one if it's still radioactive? It's going to decay again. So it will just keep continuing to decay until it gets to a stable isotope. Okay? Until it gets to a stable isotope. So, natural transmutation includes the following. Alpha, beta, positron emission. Those are natural transmutations. We're going to talk about all of those, probably getting into more of it tomorrow. The sun has a natural one, and then electron capture as well. So those are natural modes of transmutation. Okay, we'll get into it. I know you probably have questions like, what in the world is going on? As we progress, we will talk more about it. Okay, induced or artificial transmutations can also happen. These are man-made ones, sort of. Okay, so I'll let you get that down, and then we'll talk through it. All right, so induced or artificial, guys, this is occur when you take a stable atom and then you send some kind of high-energy particles to begin that reaction. Typically, it's going to be a helium nucleus. Why do you think a helium nucleus would be something that would be used? Any ideas? Doesn't have a lot of protons, absolutely. All right, so we can kind of go up by an even number there. What else, guys? What else do we know about helium? It's a what? It's a noble gas, okay? So it's a noble gas, and it's the smallest one. So all of its particles are just right there in the nucleus. It's inert, so we can kind of keep bombarding it. So typically, this is where all of those elements at the end that have crazy names like Einsteinium, Mendelevium, those are ones that typically after the number 92 there with uranium or so, they're the transuranium ones. Most of those guys are synthetic, okay? Where we, or not us in particular, but scientists, they basically bombarded nuclei that are stable with helium nuclei, and they've created other ones that were stable for fractions of a second that we can say, hey, it's a new element, even though it's not naturally occurring. Okay, so they're synthetic. They're synthetically produced. So what we do is we take a stable nucleus and we bombard it. So these are the induced transmutations, guys, where you bombard any nucleus, whether it's in the purpose of just trying to create a new element over and over, or something like fusion, where you combine two nuclei or atoms, all right, or fission, where you split a nuclei. Okay, what's the best example, guys, of fission? You all know about this. All right, you were not affected by it. It happened a long time before you were thought of. Guys, the atom bomb, right? World War II. Okay. What? They're fission, yep, because that's where they split the nucleus. They took, I forget what nucleus, I want to say it was just, you had the hydrogen bomb, which came out after, which was like 10 times more devastating than the ones used in Hiroshima or Nagasaki. Okay, yeah, go ahead. Where they split a hydrogen atom. And it's just completely decimated, as you guys can see. But that's exactly what's happening. All right. Fusion. All right. So those are the induced ones. Know the difference between them, guys. And then we'll talk more about them individually. So the symbols that we use, guys, in nuclear chemistry, you've got to know these. Fortunately for you, if you look at Table O in your reference packet, you are given the ones that I have listed here, but you're also given a couple others. Okay, we will add the couple other ones on this to the sides or below it. Alpha particle, guys, naturally occurring elements. Basically, it's a helium nucleus. The notation looks like this, which again, you have it. You don't have to memorize it. You guys are lucky. My old students, they weren't given this. They had to memorize what they all were. It's not too difficult, but you get the idea. The mass of helium. What's the mass on a helium nuclei? Or an alpha particle, I should say.
14.
Nope. 4. 14. I don't know where you got 14 from. All right. Basically, guys, there's different hazards. With an alpha particle, there's no external hazard, but there's an internal hazard. So this is talking about like on the body. Okay, externally they're not going to hurt you, but if they get inside of you, all right, that's when they can have drastic effects. All right. So the shielding. What I mean by shielding, guys, is what's going to protect you from this radiation. Your skin. Your skin will protect you from alpha radiation. Paper. Okay, so these are the least harmful of the types of radiation for us to worry about. Then we go into a beta particle. Okay, a beta particle, guys, is basically just an electron. Okay. It's basically just an electron. So we symbolize it with an E. Excuse me. No mass. It's got a -1 on the bottom.
Is that why,
Yep, mass is a 0.
on those shells they will wear tinfoil?
Yeah. Yep. So this is dangerous internally and externally for us. If you get hit with beta particles, it's going to do some damage. But the shielding is needed is just cardboard or tinfoil. So that's why, like you were saying, like they'll wear like tinfoil suits because of that type of radiation. Notice as we go down, guys, things start getting more and more drastic. Okay, the next one is a positron. Basically, this is going to mess with your minds a little, guys. Basically, it's a positive electron. Okay, it's kind of the idea there. Because it has no mass. It has no mass, but it's going to increase our atomic number. Okay, still no mass. So notice, the higher the mass is, the less impact it has, the less of the hazard. Okay, but when we start getting rid of the mass, it's basically just energy, is what it's becoming, is what it's boiling down to. So these are dangerous as well, just like beta. Notice the only difference, guys, between a beta particle and a positron is this part right here. It's either a beta particle is a -1 to your atomic number, and a positron is a +1 when we go through those, balancing those nuclear equations. Gamma rays. Anybody know the example that, where gamma rays were used? The Hulk, right? It's how he became the Hulk. Dr. Bruce Banner, he was shot by gamma rays. Let me just say this as a public service announcement. If you shoot yourself with gamma rays, you will not become the Hulk. You will die. All right? These are the most harmful, guys. Nearly all nuclear reactions deal with gamma rays because this is energy. Okay? It's only energy that it's dealing with. So we use that Greek letter gamma, and it's nothing in terms of the mass or nothing with the atomic number there, but they're very, very dangerous. They will go through everything. Okay? You need a very heavy lead suit or shield or concrete. We're talking like if you're going to make a bunker, right, for nuclear fallout bunker, guys, I think I've heard it said like 3 feet of concrete and like 10 inches of lead all around everything to stop these. It's not really going to happen, all right? We'll talk about the other two tomorrow, and then we will continue with those modes of decay and writing the nuclear reactions.